Good morning, students. Can you hear me?
Yes, sir.
Yeah, thank you for confirming it. So let's quickly review what we have seen in the last class. We have seen an introduction to convection. In this, we will see three parts regularly. That is governing law, mechanism of heat transfer, and mathematical expression. So governing law is Newton's law of cooling. The mathematical expression for this governing law is Q is equal to HA dt we have seen. And the physical mechanism is molecular diffusion and molecular collision we have seen. So this molecular diffusion and molecular collision I have explained to you here. Okay. I have explained to you in this example and this example. Okay. So Q is equal to H here delta T we have seen. We have seen H here. Okay. Where is that? Before that we have seen Q is equal to H here delta T. Each term what is the nomenclature saying we have seen Q is rate of heat transfer by convection measured in watt or joule, and A is the area with which fluid is interacting measured in meter square. Delta T is the temperature difference between the solid and fluid. It is measured in Kelvin or degree centigrade, and H being the heat transfer quotient, that is a proportionality constant here measured in watt per meter square Kelvin. And then we have seen this example. Using this example, we have understood a little bit, and then we have seen story of H. H is called as heat transfer coefficient. Its units. It is same in watt per meter square Kelvin and watt per meter square degree centigrade also. Both value will be the same. It is not a property like your thermal conductivity, and H is dependent on combination of temperature of solid and temperature of atmospheric fluid. So H is not a dependent property. H is a dependent property on viscosity, density, and temperature we have seen. And H is not a constant value for any given combination that we have seen. After that, we have solved this problem wherein you have this wire, and this wire is having so and so volt and so ampere, and if this is kept in so and so temperature room, what will be the H value, the heat transfer coefficient value we have calculated using Q is equal to H delta T concept itself. Okay, also we have seen a difference between conduction and convection. The major thing is area here. Even delta T is also an important thing. Everything is important. So area here in conduction is perpendicular to direction of heat transfer. Here in convection is area with which the fluid is interacting. So next we have seen dt. Temperature, it is the temperature difference between 2 points in one solid when it comes to conduction. But when it comes to convection, temperature difference between solid and fluid. Also we have seen the proportionality constant. And then somebody asked me a question. I have explained that question using this equation. This is called as Juttis-Boelter equation. So this is what we have seen in the last class. In today's class, let us start an introduction to radiation. We have seen that there are three modes of heat transfer, that is conduction, convection, and radiation. And today we shall look at an introduction to radiation. Radiation. So as a regular story, what we have is, first we have to see what is governing law, and then we have to see what is physical mechanism of heat transfer, and then you have a mathematical expression. So the governing law when it comes to radiation is, it is Stephen, sometimes it is written as F also, Stephen Boltzmann law, B-O-L-T-Z. Yeah. Stephen Boltzmann law is the governing law here. And what is the physical mechanism of heat transfer? It is electromagnetic waves, which are also called as photons. Okay, through this physical mechanism of heat transfer happens. And mathematical expression, what it says is Stephen-Boltzmann law states that heat transfer by radiation is proportional to the area, and also the Q is proportional to fourth power of temperature. Fourth power of temperature. So Q is proportional to the fourth power of temperature. Combining these two, what I get is Q is equal to sigma into A into T to the power of 4. This will be my mathematical expression. Okay. So this is what in general introduction to radiation. These things you have to remember. Let's look at what is the physical mechanism of heat transfer first. Okay. Let us take a body here. Okay, let us take this as a room. Okay, there is a big room here. In this room, there is a small body. Okay, let us say your cell phone is there. Your cell phone is there, and this cell phone will be having so and so temperature, and this temperature emitted by this will be influenced by the temperature of the walls of the room. Okay, so here let us say your cell phone is at 40 degrees centigrade and your walls are at 20 degrees centigrade. If this is the case now, what happens is there is a net radiation heat transfer between these two bodies here. That is, there will be something called as electromagnetic waves. These electromagnetic waves will be taking the energy from here to here. So in the form of energy packets called quanta, the energy is transferred. That we call it as an electromagnetic radiation. Okay. So when I say the electromagnetic radiation, I am referring to a wavelength range of 0.1 to 100 micrometer. Okay. So that particular range only we will consider in our thermal radiation thing. Right. So this is how the mechanism of heat transfer will be. So there will be any given body will have temperature. Any given body having so and so temperature will be emitting so and so radiation. So that is what is said by your Stephen-Boltzmann law. This is what is represented by Q is proportional to the fourth power. Okay. Now, when I write this Q is equal to sigma into A into T to the power of 4, no, what it is saying is, it is saying that Q emitted by a given body. You have Q, this is a body 1, this is your body 2. Okay, now if I write it for Q2, it is sigma into A into T power 4. This will be T1, this is T2. So what I take here is a black body radiation actually, but when I take net now, this will be sigma into A into T1 to the power 4 minus T2 to the power 4. So this is how your equation will become. Also, this Q net is dependent on the emissivity of the material. Q net is dependent on the emissivity of the material. So sigma into A into epsilon, which is meaning emissivity is also introduced into this equation. So it is T1 to the power 4 minus T2 to the power 4. This is the equation that you should remember in this case. Okay, so this is your equation here, right? So Q net is equal to sigma into A into epsilon into T to the power of 4 minus Q to the power of 4. This is the equation. So what is the Q here? It is the rate of heat transfer by radiation, and it is measured as usual in your watts, which is also called as joule per second. So that is your Q. What is sigma here? It is a proportionality constant that you have taken. Okay, let us write this at the end. First, let us focus about area. What is the area here? Okay, here I have two bodies in this example itself. That about example I told you, two bodies are there. When I am taking Q with respect to this body, so this Q1 to 2, if I am taking, no, the emitting body will be taken into consideration, and this is the receiving body. Emitting body is 1, the receiving body is 2. So T1 to the power of T2, you have taken. The area also will be of A1. So what is this area? Area of emitting body. Okay, it is the area of emitting body. It is measured in meter square. Right. Then what you have is epsilon, which is emissivity. And the unit for this emissivity is no unit. There is no unit for emissivity. It's a constant value and it varies between 0 to 1. And this epsilon value is equal to 1 for black body. And this epsilon value is less than 1 for gray body. Gray, I can take gray body. So this is your epsilon. And then what you have here, you have T1. T1 is temperature of emitting body. And this measure in Kelvin. This is very, very important. This is measured to be only in the Kelvin, not in degrees centigrade. Not in degrees centigrade. This should not be taken in degrees centigrade. It should be taken only in Kelvin, because here you are not considering the delta T. If you are considering the delta T, plus 273 and minus 273 will get cancelled. Whereas here in this particular equation, you don't have that. In this equation, you have T to the power 4. So in SI units, it should be Kelvin. Then you move on to T2. It is a temperature of receiving body. CEIB. Receiving body is also in Kelvin. This is very important. Kindly keep this in mind. It should be measured only in Kelvin. The Kelvin value should be substituted in this equation. Now let us move on to the proportionality constant sigma. This sigma is called as Stephen. Sometimes it is written as F. Don't worry. Stephen Boltzmann constant. The value of this Stephen Boltzmann constant is sigma is equal to 5.67 into 10 to the power of minus 8 watt per meter square and Kelvin power 4 you will get here. Okay, how do I get this? Using this equation itself. This is measured in meter square. This is measured in Kelvin power 4. This is measured in watts. So watt per meter square Kelvin power 4 I got here. Watt per meter square Kelvin power 4 is your Stephen Boltzmann constant. There is a simple way to remember this. It is simply 5678. 5678. 5.67 into 10 to the power of minus 8 is the value actually. But if you remember 5678, you can remember Stephen Boltzmann constant very easily. 5678 is the code to remember your Stephen Boltzmann constant, right? So that is the story of your mathematical expression when it comes to the radiation. So the mathematical expression is also done. Its governing law is Stephen Boltzmann law, and the physical mechanism of heat transfer is electromagnetic waves or photons. And then when it comes to mathematical expression, so this is the story. Now let us move ahead and look into a simple problem. Okay, let me take a problem. Where is that? Yeah. So here is your problem. This problem, what you do is you try to take a snapshot now, maybe in your PC or cell phone, and then once the class is over, you can make a note of this problem also in your notes. Now, the problem goes this way. Consider a person standing in a room. Okay, what it is saying is, consider a person standing in a room. Okay, let us take a room here. And in this room, there is a person standing. Okay, this person standing. And then the room temperature is 22 degrees centigrade. Okay. Then the inner surfaces of the walls, floors, and the ceiling of the house are observed to be at an average temperature of 10 degrees centigrade in winter. So whatever the average temperature of this walls, ceiling, and then floor, it is observed to be at 10 degrees centigrade temperature in winter is 10 degrees centigrade. And the same thing is (25 degrees centigrade in summer. Okay, this is the value. Also, is asking you to determine the radiation of heat transfer. Q radiation. What is the value he is asking? Radiation heat transfer between what and what with this person and surrounding surfaces. Okay, so the surfaces. If exposed surface area and the average outer surface temperature of the person are 1.4 meter square. So this person is having 1.4 meter square area and his temperature is 30 degrees centigrade. Normal human body temperature will be around 35 degrees centigrade. But anyways, in this question it is 30 degrees centigrade. It is given here. Okay. Now, this is what is given in question, and he is asking you to find Q radiation. And this Q radiation you can find out in two cases. It is between person and surfaces. Person and surfaces in winter you can find. This is first case. And the same thing, Q between person and surfaces in summer also you can find, because he has given two temperatures for the wall, so you can find these two things here. So this is measured in two different things. Let me take the first thing as Q winter, which is equal to sigma into A into epsilon into T to the power of 4 minus T to the power of 4. So let us call this one as person, and this will be surfaces. So the sigma value is 5.67 into 10 to the power of minus 8 into area is 1.4 given in question. See, the epsilon value he has not given in the question. If he is giving you in the question, you take that value. But in this particular question, he has not given. So what you can consider is it is 1. Okay, if it is given, you have to take it. If it is not given, you cannot take it. So you can take it as 1 for now. But strictly speaking, when it comes to examination, what you have to do is you have to use this data book Go to the data book and you may use the value that is there in the data book. So let me not use one. One is a black body. Your human body cannot be a black body. So what I can take it like is 0.7, let us take. Okay. Let me take 0.7. And then the temperature of the person is given as 30 degrees centigrade. And this 30 degrees centigrade, I have to convert into Kelvin. 30 plus 273 whole to the power 4 minus temperature of the surfaces in winter, it is given as 10 in the question. 10 plus 273 to the power 4, and then close the bracket here. Then this is the bracket. Now, what is this value? Somebody please calculate and tell me. The same way you'll get it for Q in summer also. It is 5.67 into 10 to the power of minus 8 into the area is 1.4 meters square, and this is 0.7 into the person is 30 plus 273 whole to the power of 4 minus this 25. The summer temperature is given as 25 in the question. Is it 25 only? Yeah, it's 25 plus 273 whole to the power of 4. Okay, so tell me these two values. Somebody calculate it. Yeah, it is 111.94 watts in your winter, right? Darshi, is it for winter?
Yes, sir.
30.16, thank you, Darshi. And 30.16 is for summer. So, from this, you can see this value is around 110 or 112, and this is 30. See, if you take the values here, from these values, what can you understand? Look at these values. The Q value that is there in winter, Q value that is there in summer. So from this, can you understand anything? Can you infer anything? You imagine yourself in a room that is at 22 degrees centigrade every time. Okay, you are air conditioning it, it is maintained at 22 degrees centigrade. And the walls, you cannot maintain at so and so temperature. They will be defined by the atmosphere temperature. So the walls are at 10 in the winter and 25 in the summer. If this is the case, these are the values you are getting. So from these values, what can you understand? Can somebody tell me? In winter, the value is so huge. The radiation heat transfer is so huge. In summer, it is very less. So from these values, can you understand anything? Can somebody say it? Take a little time and yeah, T decreases and Q increases. That's good. That's right. See, the thing here is that you should understand here is what you understand. See, in winter, what happens? It is very chilly. You will feel very much chilling. Okay, and then in summer, you will feel that it is warm. Why you are feeling that it is chilly and why you are feeling that it is warm in summer? Because there is a radiation heat transfer happening between you and your walls. Between you and your walls. Okay. Although the radiation heat transfer between you and your air is same during the winter and summer, but the radiation heat transfer between you and your walls has changed in winter and summer. Okay. Even if the temperature is same in the winter and summer, you will feel the difference of this winter and summer because of the radiation heat transfer between the walls and your human body. So that is the reason why there is a chilly feeling even if the temperature is maintained at same value in your winter and in summer. So in winter, radiation heat transfer between you and your walls is very high when it compared to the summer. That's why you will feel that chilliness in winter and warmness in your summer. So that's the point here, right? So that's what you can understand from these. Somebody is writing, sir, if the mobile, can you repeat that question? It went off. Sir, if the mobile temperature is high, then radiation is also high? No. High or low? So you are Darshi, you are speaking about this cell phone, right? When you say that it is
Yes.
a mobile. Yeah. See, cell phone temperature is high, then the radiation is also low, is also high, is also high or low. What kind of question? Can you clarify that? See, the question is not so clear.
Then the radiation will be high or low.
Then the radiation heat transfer will be higher or low. You can understand from this expression itself. Here, yeah, if you are taking between the mobile and the room walls, and the room walls are at same temperature, and if you are increasing the mobile temperature, so the delta T increases. If the delta T increases, Q will also increases. Q by radiation also will increase. It is as simple as that. So you can look at this expression. Always refer to the expression. What I tell you is, whenever you are trying to understand any given heat transfer, try to look at that mathematical expression. You will understand a lot of things. So the mobile temperature is increasing, the delta T will be increasing. See, here delta T is not simple delta T, it is power 4 and then difference. Even that case also, the temperature change will be more if the mobile temperature is increasing and the wall temperature is constant. Then Q will increase. If this is decreasing, no, this will decrease. It is as simple as that. Okay. So this is what we will learn from this practical example. Okay. This is not just a problem I tell you. This is a practical example. This is actually in meter square. There is a typo here. Right. Moving on, let me take one more example. This is not a problem, mathematical problem. This is just a simple thing for us to understand. So can you see this image? I hope you can see this image here. Can somebody type what is this?
Water heater.
It is solar water heater. Okay. It is solar water heater. All right. What kind of solar water heater it is? There are so many kinds of solar water heaters. This particular thing, what kind of thing is it? See, many of the times you will see a plate here. Okay. That is called as PV plate. Okay. Photovoltaic plate you will have here. That photovoltaic plate will be collecting the solar radiation. But here you don't have that. Here you have a tube. And this tube is called as evacuated tube. Evacuated tube solar water heater. So this is evacuated tube solar water heater. So if you understand, if you take this particular thing, if you understand this part now, we will understand the radiation heat transfer like anything, the concept. Same. Here this tube is actually having two parts. This is the outer tube and then the inner tube. There are two tubes placed here. Okay. This is the inner tube. This is the outer tube. And the space between these two tubes is evacuated. So what we have here is just vacuum. Okay, and the beauty with your radiation heat transfer is radiation heat transfer can happen even in vacuum. Even in vacuum, this radiation heat transfer can happen, whereas your conduction and convection cannot happen in your vacuum. Okay, radiation can happen with the bodies, and without any body also radiation heat transfer can happen. That is the beauty with your radiation heat transfer. Now coming to this point, now what happening here? Here in this tube you will have water here. There is water here and there is a vacuum here. So this material, the inside tube, how is it made? It is made such that the solar radiation is taken so much by it. Okay, it will be a very good absorber. Okay, very good absorbing material is coated over this inner tube. That is the reason why lot of heat will be taken, lot of solar radiation will be taken by this, and then water will get heated up. Okay, so while it is coming here, it will go only in this direction. It cannot come out. Why it cannot come out? Because there is no material here. There is no air here. There is no medium here to come out. So that's why whatever the heat that is entering in will stay inside. It will not try to come out because it is purely vacuum. It has to come out by conduction or convection. The conduction cannot happen. The convection cannot happen. Only radiation can happen in this case. That's why what you are doing is you are actually trapping the heat here inside this and then heating it. When you heat it up, no, what happens is whatever the water that has come down here, the cold water will get heated up because of thermosiphon effect. Thermosiphon effect. When I say thermosiphon effect, it is natural effect wherein due to the temperature difference, the high temperature body will try to float over and the less temperature body will try to come down. So high temperature water, hot water will go up and the cold water will come down, and again the cold water will get heated up. It will go up, and as per the utilization, this cycle speed varies. So did you understand this concept? Is it clear? You have any questions at this level? No questions?
No, sir.
Okay, so Chaitanya, thank you for that. I hope this radiation effect is also clear to you.